Right, so to start this video off, we're going to have a chance just to practice with some unit vector notation. So the first thing I want you to do, you see I've written vectors A, B, and C. A is 5 meters, 30 degrees north of east. B is 10 meters, 45 degrees north of west. And C is 8 meters, 6 degrees south of east. Let's go ahead and write each of these in unit vector notation. Okay, so I've gone ahead and done this for all three vectors. Just so for each of them, you're just using sine to find the j component and cosine to find the x component. If you're confused about this or still having some trouble with this, you should find some time to come in so we can work on it and do some more practice together. Okay, so we've got these three vectors now written in unit vector notation, and what we're going to go ahead and do is do some vector addition. So what I want to do here to start this video off is find the sum of vector A, B, and C. So if we're going to go on a short journey in which we go 5 meters 30 degrees north of east, 10 meters at 45 degrees north of west, then 8 meters at 60 degrees south of east, I want to know where I end up, like what my displacement is, how far I am from where I started. Okay, so what I would do is basically just draw A, which is 5 meters at 30 degrees north of east, so maybe something like this. And I'm just kind of sketching them, these are not perfect. And then from there, at the head of this one, I'll start the tail of B, 10 meters at 45 degrees north of west. So this is the x-axis, 45 degrees would be something like this. So we got like 10 meters this way. You can see some really straight lines here. And then vector C is 8 meters at 60 degrees south of east. So we're going to go, if this is east, 60 degrees would be like here somewhere. We go 8 meters, and so we end up like right here somewhere. And so to estimate the sum of these, we'd say it's something like, it would be basically like this would be our resultant. So we end up right there. I'm going to just give it an estimate, say this is like, maybe like 3 meters. And we'll say about 70 degrees north of east. And this is just a complete guess. We'll see what it is. So the way we can find this, the more efficient way of doing this is using the unit vectors. So what we can do is basically to add A, B, and C, we'll start by adding, and we'll call the sum of them vector D. Okay, so vector D would be equivalent to the sum of all the I components plus the sum of all the j components. So that'd be 4.3 plus negative 7.1 plus 4, and then over here it's going to be the j components, so 2.5 plus meters, 7.1 meters minus 7.1 meters. Okay, so we'll go ahead and simplify and get vector D in unit vector notation. Okay, so we get this, and then I just realized I made a mistake and checked my math, and so this is actually, I believe, should be 6.9, which means that this would be a negative 6.9 right here, which means that this would be 2.7 meters. Okay, so vector D, 1.2 meters I, 2.7 meters J. We can go ahead and write it in magnitude direction notation. So that's going to be, for the magnitude, the square root of 1.2 meters squared plus 2.7 meters squared. And the direction is going to be inverse tangent of opposite 2.7 over adjacent 1.2. Okay, and so we're going to get that vector D is about 2.95 meters, and it's 66 degrees north of east. Alright, and before we continue, I'm just going to say I actually was really close with my estimate here. I'm pointing this out because I'm surprised at how close I actually was, considering, as you can see, what an awesome job I did drawing those. I promise that I did not know what that was before I drew them. So anyway, Moving on. So this is, I hope you can kind of see the benefit of using the unit vector notation for adding vectors, because it allows us to kind of use what we know about one-dimensional stuff and then put it in 2 dimensions. So like displacement in 1 dimension, we go 4.3 meters horizontally, then we go back 7.1, and then go 4.1 forward. Okay, so if we were to draw this out, it would look something like this. We go 4.3, then 7.1, and then 4, and that would be for x. And then for y, it's going to be something like 2.5, and I'll do it over here so it doesn't get too confusing. 2.5, and then 7.1, and then 6.9. So then this is our y component, and this right here would be our x component. Okay, from tail to tip. So from tail to the ending tip, from the tail to the ending tip. That's how we draw those vectors. Okay, and so we just really are focusing on one-dimensional stuff here. Okay, and that's what really allows us. That's why the unit vector notation is something that's useful for us, and that's something we use quite a bit in physics. Okay. Okay, so the next thing we can do is we can actually multiply vectors by a scalar. Okay, and so a scalar is just some amount, some quantity, and it's called a scalar for the very reason that it's used to scale a vector. So a scalar is something that scales a vector, making it bigger or smaller. It kind of stretches it. So if we're going to take vector A and we're going to scale it, let's say we scaled it 3 times, we would stretch it until it's 3 times bigger. Or if we were going to scale it by a number smaller than 1, we would compress it until it got to that size. Okay, and if you want to get really, really technical with unit vectors, the unit vector for is something like this. It would be something I plus something j plus something k, and then we scale it with these quantities. So we scaled for A, we scaled at 4.3 in the I direction and 2.5 in the j direction. So we stretched I from being just 1 to being 4.3, and we stretched j from being 1 to being 2.5. Okay, and so that's kind of just something really, really technical that we don't need to really worry about, but that's kind of what it means to scale something. And so if we want to scale vector A, let's say we want to scale it by 3. Okay, and so we could then take vector A and multiply it by 3. So we would say 3 times 4.3 meters for the I direction, so we're just going to multiply each component times 3, and 3 times 2.5 for the j direction. Okay, and so we get something like 7.5 meters j, and 3 times 4.3 would be 12.9 meters I, and that would be equal to 3 times A. So graphically, if this is vector A, if we're going to scale it by 3, it would look something like this, 3 of A. Okay, and so our new vector would look like this. So it's 3 times the length of A in the same direction. Well, same thing's happening here, except instead we're drawing this horizontal component 3 times, and we're drawing this vertical component 3 times, so we end up in the same place. Okay, and so it's kind of the way that we can look at what we're doing when we multiply the components. Okay, and then if we were to scale it by, say, a negative number, then we would flip it around and draw it the other way. Okay, and then you can actually kind of combine them together too. Okay, so the last thing we're going to do here is we're going to do a fairly complex vector addition problem in which we add vectors a and b. We're not just going to add them. We're going to find 2a minus 4b. And I want to know what that result is in magnitude direction notation. Okay, so that's a whole lot, but I'm going to walk you through it step by step. So the first thing we need to do is we need to scale vector A and vector B by these scalars. So let's go ahead and multiply vector A by 2 and vector B by -4. So go ahead and work that out. So 2a that you would have found would have been just 2 times each of those components. So 2 times 4.3 is 8.6. 2.5 times 2 is 5. And then for vector b, -4 times b, so it would be 4 times -7.1. And, sorry, -4 times -7.1 giving us positive 28.4. And then -4 times positive 7.1 giving us negative 20.4. Okay, so finally, we want to combine them now. So 2a plus -4b, we're just going to go ahead and find the sum of these. Okay, and that's going to give us 2a plus -4b. Alright, so go ahead and find that. You should get, let's see, 37 meters I minus 22.4 meters J. Okay? And then the last step here is going to be to write this vector in magnitude direction notation. And so we'll sketch it out real quick. That would be 37 meters for the I direction, and then negatives will go down 22.4 for J. So let's go ahead and find the magnitude of our resultant vector and its direction. Okay, so to find the magnitude, we did the Pythagorean theorem here. We got about 43.3 meters. And then to find the direction, we used inverse tangent with the opposite over the adjacent side and got 31.2 degrees. Okay, so that would be the magnitude and the vector and magnitude and direction, of our resultant vector.